Okay, I think Ron, you can start.
Okay. So, morning, everyone. It's a pleasure to see that we have already more than 350 participants. And it is a great pleasure to introduce today's speaker, Noga Alon. Noga started his academic journey here at the Technion as an undergraduate student, and he went on to become a world-leading mathematician and theoretical computer scientist. Noga solved many open problems in combinatorics and graph theory, and while doing so, he introduced and developed techniques that have become part of the standard toolkit of every researcher in these areas. These include the probabilistic method, the polynomial method, and much more. Several of Noga's results are highly applicable. For example, he wrote a paper named Splitting Necklaces about 40 years ago that has taught generations of thieves how to split stolen necklaces among them fairly and efficiently. Noga received many prestigious prizes. The first one was the Erdős Prize, established by Paul Erdős, whose name you see in the title of the talk today, in memory of his parents. And then came many other prizes. Two of the more recent ones are the Shaw Prize and the Wolf Prize. Noga also got a few honorary doctorates. Of course, the most important of them is the one from the Technion, which he was supposed to be awarded yesterday. But unfortunately, the ceremony had to be postponed, and for the same reason, this talk moved to Zoom. Noga is a professor of mathematics at Princeton University and a professor emeritus in the Department of Theoretical Mathematics and in the School of Computer Science and AI at Tel Aviv University. And his expertise in AI will play a key role in today's talk, titled Erdos Problems and Speculations about the Power of AI Models. Noga.
Thank you, Ron, for this very nice introduction. I hope this will not be the only attractive part of this lecture. And it's always a pleasure to speak at the Technion, even if in this time only online. So let me thank the organizers for the invitation and thank you all for participating. I'll talk about Erdős problems and speculations about the power of AI models. And let me start with a few slides about Erdős and Erdős problems. Incidentally, at the end, we will have time for asking questions. But if you have really pressing questions during the lecture, you can try to write in the chat. And maybe Omri will tell me about it. So let me just... so something about Erdős. So Paul Erdős was an influential Hungarian mathematician with a remarkable ability for formulating challenging open problems in many areas of mathematics, including discrete mathematics, graph theory, number theory, mathematical analysis, approximation theory, set theory, and probability theory. he used to wander around the world, and in particular, he had a permanent visiting position at the Technion, where he could visit whenever he wanted to, and he used to visit quite a lot. And actually, the first time I met him was during one of these visits. I was still a teenager. I was in high school, but my mother was a good friend of someone in the administrative staff of the Faculty of Mathematics. And she used to take care of Erdős when he was visiting, and I first met him in her apartment. He told me some questions, and I told him about some ideas I had. I was interested in mathematics in a very early age, and he kind of pretended to be impressed. And it took me about a year to realize that everything that I told him about my ideas was totally trivial for him. So it was clear that he knew everything, but for him it was important to encourage children interested in mathematics. So he kind of pretended to be impressed. Here is another less formal picture of Erdős, and I wrote here a quote from one of his papers. So he wrote quite a lot of papers about open problems, so just a list of problems. And one of the nicest papers of this kind was in the inaugural volume of Combinatorica. This was published in 1981, and the title was On the Combinatorial Problems Which I Would Most Like to See Solved. And a quote from there is that a subject needs challenging, unsolved, and not quite hopeless problems to keep alive. And indeed, the problems of Erdős were often not impossibly difficult. So it was in many cases possible to make progress in their study and even to solve some of them, as I'll mention later. And actually, this is better than hopelessly difficult or impossible problems in encouraging research. And indeed, I think it would be fair to say that many of his questions shaped the development of quite a lot of areas of mathematics in the 20th century. Here is another interesting kind of statistics about a database which is maintained by Thomas Blum. He's a young mathematician in Manchester, in England, and he maintains a database of open problems of Erdős. So he goes through the open problem papers and other papers and collects all the problems, trying to avoid duplications, and trying also to find out which problems have been solved. You know, some of them have been asked more than 80 years ago. So at the moment in this web page, he has a bit more than 1,200 problems, and 550 of them have been solved. So you see, quite close to half. Now, Erdős used to offer monetary awards for solving some of the problems that he liked in particular. And the total value of the solved problems reported in Blum's database is $22,163 out of a total of $59,733 offered. So the total value of unsolved problems is currently a bit over $37,000. I thought to convert it to Israeli currency, but somehow the rate of exchange keeps changing, so I kept it this way. And I should say that this is probably not the easiest way to make money, but still it can be a good one. Okay, so I'm going to talk mostly about two open problems suggested by Erdős that have been solved recently by AI tools. And I promised that this lecture will not be too technical, but still it's a lecture about mathematics. So there would be some mathematics, but at least the formulation of the problems is very simple and should be understandable to everybody. So here is the first problem that I want to mention, and I called it planar sets with no 3 on a line. And here is one way to formulate it. So suppose we have a set of points in the plane, like the set of red and green points that you see in the bottom. And suppose that it has the following property. Whenever we take a subset P of this set of points, then this subset contains inside it a subset P prime of at least half the points of P with no 3 points on a line. Okay, so this is the property that we want to assume. And if you look at the picture below, you see in the picture below I have 11 points, 6 of them are red and 5 of them are green. And it's easy to see that among the red points, you don't have 3 on a line. And among the green points, you also don't have 3 on a line. So this implies that whenever we will take a finite subset or any subset of points among these 11 points, then at least half of them will be red or at least half of them will be green. And because of this, at least half will have the properties that no 3 lie on a line, right? Because this is the situation with the red points and with the green points. And the question is it true that this is always the case? So suppose we have this set A so that every subset of it contains at least a half with no 3 points on line. Can we partition it into 2 sets, A1 and A2, like the red and the green here, so that each of them contains no 3 points on a line? Well, maybe this is too strong. So if not, is it true that A can be partitioned into 1,000 such sets? So you should think now about A as a big set of points, many points, and they have again the same property. Whenever we take a subset, it contains a half with no 3 on a line. Can we always partition such a set into at most 1,000 sets AI so that each AI contains no 3 points on a line? So this is essentially a question asked by Erdős, Neshetril, and Redel, two Czech mathematicians in the early 90s. And here I wrote it in a more formal way. They ask it in a slightly more general way, but you don't even have to read it. It's essentially equivalent to what I said with the example of half and the partitioning into 1,000. And it turns out that the answer here is no. Namely, there are examples that satisfy the property, and still we are not able, it's impossible to split the set of points into 1,000 subsets, each having the property of having no 3 points on a line. So this was solved by an internal model at OpenAI, and this was in February of this year, so a few months ago. And it's a very nice short solution, and I want to tell you something about it. So this will be a little bit more technical, but not too much. And And even if you don't really follow, hopefully you get the flavor of things. So here is the theorem that the AI model proved. So it proves the following. For every integer k, so you can think about the integer k as a pretty big integer, possibly the 1,000 that we had before, we have a set A of 3 times k factorial square points, so some finite number of points in the plane, so that it has the property that I mentioned, namely every subset of it, you can find half of it, in fact, even more than half of it, which contains no 3 points on a line. And on the other hand, you cannot partition A into k sets AI so that none of them contain 3 points on a line. Whenever you partition A into k subsets AI, one of them will contain 3 points on a line. So this says that the answer to the question before was no, in a very strong sense, even if we change 1,000 to any finite number. And I want to tell you something about the proof that was found by the AI model, because it's short. Well, maybe to really understand it exactly, you need a little bit of a background in combinatorics, but as I said, even if you don't follow the technical details, hopefully it tells you something about the flavor of things and how short or complicated or simple the proof is. So here is again the theorem, and here is a sketch of the proof by the model. Okay. So we want to construct this set of 3k factorial points square. So what we do is that for each pair of integers, I and j, where both I and j are between 1 and 3k factorial, we define a point, and I denote this point by P sub ij, with index ij. So a point in the plane has 2 coordinates, the x-coordinate and the y-coordinate. So the x-coordinate is ti plus tj. The y-coordinate is ti squared plus ti tj plus tj squared, where the reals ti's that we choose are algebraically independent, and one way to think about it is that we just choose random numbers between 0 and 1. So they will have this property. So once we choose these 3k factorial random numbers between 0 and 1, it enables us to define all these 3k factorial square points, Pij. Now, it's good to think about the pairs ij as representing the edges of the complete graph on k vertices. So we have this complete graph on 3k factorial vertices. For each pair of points, we have the edge connecting them. And you can think about the point Pij, that it is indexed by this edge or it is sitting on this edge. And then there is something that is easy to check. So using just what we study, say, in first year undergraduate course on linear algebra, say. So 3 of the points Pij, they lie on a line, even only if the corresponding 3 edges form a triangle in the complete graph. So if the 3 points are Pij, Pil, and Pjl, corresponding to 3 edges of a triangle, then the 3 points lie on a line, and in any other case, they do not. And this is simple to check. I'll not show it, but there is a simple linear algebra condition for 3 points to lie on a line. We have to look at some determinant, and this will tell us that the statement is true. Now, once we know this, the 2 properties we need from the set follow as follows. So if we take a subset P of the points, the fact that it contains more than half of its points with no 3 on a line just corresponds to the fact that any set of edges, so they define a graph, and any graph contains what is called a bipartite subgraph, so a subgraph with more than half of the edges that does not contain a triangle, in fact does not contain any cycle of odd length. With just one way to see it, so this is a folklore simple result. In graph theory, one way to see it is to split the vertices of the graph randomly into 2 parts and take all the edges with one endpoint in one side and another endpoint in the other side. So this will not contain a triangle, and in expectation will contain half the edges. So this is one property. And the second property is a special case of a basic result, again, in extremal graph theory, so result proved about 100 years ago by Frank Plumpton Ramsey. And a special case of it says that whenever we have a big complete graph and we color the edges of it by k colors, then there would be a monochromatic triangle. If the graph we started with is big enough, we would find a triangle with all edges colored of the same, with the same color. And in fact, the upper bound known for this Ramsey number, which we denote by R333 k times, is less than 3k factorial. So if we have all those points that we described, so they correspond to the edges of the complete graph, partitioning them into k classes corresponds to a coloring of the edges by k classes, and then the fact is that we will have a monochromatic triangle. So again, I apologize if this was too technical for some, but hopefully you get the impression that this is relatively short and rather simple. And as I said, this was generated by an internal model at OpenAI. This was in February, and it's kind of a nice proof, but there are some reservations here that I want to mention. So the first is that the result is not really surprising. Anybody who thought seriously about problems of this type, and there are problems that are similar, would kind of tend to expect that the answer is no. Second, maybe more serious, is that the result actually is known in some sense. So it follows from a theorem in a recent paper by Reiher, Redel, and Sales. Still, I should say that the model's proof is better, is simpler, and it provides better estimates, but still this was basically known. Another reservation is that the problem itself was hardly known and received little attention. Actually, in February, when they just found it in OpenAI, then someone there sent me a message about it and asked me what I know about this problem, and I didn't hear about this problem before. I knew several similar ones, and using this, we could find what exactly was known and what was similar. But I think that not too many people thought about it. And finally, that the proof of this result is rather similar to known proofs of similar results. So this was a nice proof of an open problem, but not really impressive. And I should say that around the same time, there were several additional examples of research open problems proved or solved by AI models, starting maybe from December of last year until February and March of this year. There were some modest successes of examples like this. So this was the case until last month, until maybe May. In April, I should say, there was some maybe a more impressive success about some problem in number theory. that did receive some attention, but still was not really spectacular. And somehow a breakthrough really happened in May, so about a month ago. In fact, I checked, and the email message I got about it together with some other people was in May 8 of this year. And this has to do with the unit distance problem. So that's another nice geometric problem, and I want to tell you something about it. Okay, so what is a unit distance problem? Again, it's simple to understand it. For an integer n, we denote by u of n the maximum possible number of unit distances determined by n points in the plane. So we take n points, we try to place them in the usual Euclidean plane, and we try to have as many pairs of points as possible that have the same distance, and then we can scale it so that this popular distance is distance 1. So for example, if you look at this picture here, it shows you that u of 4 is 5. You see, if you have 4 points, then we can put them like you see here, that the two triangles sharing a common base are equilateral triangles. So all the 5 black edges that you see here are of distance exactly 1. But this already determines the distance between the topmost and the bottommost point, and you can check that it is square root 3, which is not 1. Namely, we cannot have all the 6 pairs having the same distance, but we can have 5. And in fact, for small values of n, this maximum possible number of pairs determining the same sequence was computed exactly using computers with no real AI, so just some exhaustive search. It's clear that these are finite problems. And you can see here a table of n and un for the values up to n equals 21. So you see that when you have 21 points in the plane, then the maximum number of times we can have the same distance is 57. And you can also see, if you look at this table, that the ratio between u of n and n keeps increasing. So at the beginning it is 1, the ratio, then here it becomes 2, and later it's almost 3. So it looks that it grows maybe a little bit faster than linear. Okay. And the problem of Erdős, raised in 1946, is what is this u of n for large n? So he was always interested in the asymptotics, and in particular, he wanted to know if u of n is not much more than linear. Is it n to the 1 plus little o 1, meaning that for large n, it is less than n to the 1.0001, right? So it cannot be more than n to the 1 plus epsilon for large n. And there were known upper and lower bounds. So the lower bound appears already in the original paper of Erdős, and it's given by a scaled grid. I'll talk about this a little bit more soon. And this lower bound is a little bit more than linear. So it's n raised to the power 1 plus constant over log n. So you see that log n, as n is big, is also big, but is much, much smaller than n, right? So n has to be very big so that log n will be somewhat big, and the constant over log n that you will see here will be less than, say, 1 over a million. But still, for large enough n, this is the lower bound. And the upper bound is some constant n to the 4th thirds. This was first proved by Spencer, Semerade, and Trotter, and since then there have been many other, maybe simpler proofs, and the nicest is by Laszlo Szekely, found nearly 30 years ago using some clever tools about what's called the crossing number of graphs. So the conjecture that was raised in 1946 and was open until last May, was that this u of n, this maximum is not much more than n. It's just n to the 1 plus a tiny bit. And this was really a well-known problem. So just a few comments about it. So first, I said that Erdős used to offer monetary rewards for solving the questions he liked, and he offered $500 for a proof or disproof, which is quite a lot. Then there is a book by Peter Brass, Leo Moser, and Janusz Pach called Research Problems in Discrete Geometry, published about 20 years ago. And there it is written that this problem is the best known problem in combinatorial geometry, which I think is fair to say. Here is another comment about it. So we had a recent paper last year, published last year with Matija Vucic and Lisa Sauerman, following some ideas of Matuszek. And there, without saying something very rigorous, let me say that if we ask the analogous problem where the distance is replaced by some other notion of distance, so not the usual Euclidean distance in the plane, then there is some way to define what we mean by most ways to define a norm or a distance, a nice distance in the Euclidean norm, so it's most in the bare categoric sense. And for most distances, the answer to the problem is n times log base 2 of n. So really not much more than linear in n, and maybe this gave evidence to think that something like this should hold also for the Euclidean plane. So as I said, this was a prevailing conjecture. And then in May, so last month, an internal model at OpenAI basically solved the problem and showed that the conjecture is incorrect. Namely, there exists some positive constant c, so it's independent of n, so that the maximum number of unit distances that can be determined by n points in the plane is at least n to the 1 plus this constant for infinitely many values of n. And this was impressive for several reasons, and let me list them. So first, this was really the first example of a mathematical result proved by an AI model which settles a well-known old problem that has been considered for many years by lots of leading mathematicians, human mathematicians, with no success. So I think it would be fair to say that anyone working in discrete geometry thought about this problem, and many mathematicians working in other areas at least spent some time thinking about it. Now, another impressive thing is that the proof applies fairly deep results from algebraic number theory, so from a different area, which is not really geometry, but is a number theory. And somehow it's not so clear how what is the connection between these two areas, although I'll try to describe something about it. So, and another thing that I mentioned also before is that the result is unexpected. So pretty much everybody believed the prevailing conjecture. So the intuition of most experts here was wrong. Now, I want to say something about the construction and the proof, but I'll say very little, and it will be mostly in terms of the relevant buzzwords. But let me first tell you something about the simpler grid construction of Erdős, which suggests that there is some connection to algebraic number theory. So the construction is really just a grid. We take a square root n by square root n grid, like the one you see here, and we take all the points that are intersection points of a horizontal line and a vertical line. So we have here like square root n rows, and in each row we have square root n points. Now, why is this good? So look at the following. Here's just an example. You see that 4 square plus 7 square is 65, and this is also 1 square plus 8 square. Okay. And because of this, by the Pythagorean theorem, which we learn in elementary school, I guess, the result proved well over 2,000 years ago, the following red lines here all have the same distance, same length, which is the square root of 65. So here is you see this line, I went here horizontally 1 and vertically 8. So the Pythagorean theorem tells me that the square distance of this is equal to the square of 1 plus the square of 8, which is 65. And what about this one? Here I went horizontally 4 and vertically 7. So the sum of their squares is again 65. So the length of this is also the same. And then I can also go horizontally 7, vertically 4, or horizontally 8 and vertically 1. And all these lines have the same distance, the same length. Right? So that, and you can actually also reflect it to the left and to the bottom. And so this shows that really if we took a big grid, then every point of the grid, which is not too close to the boundary, is of distance exactly square root of 65 from 16 other points of the grid, the 4 that we see here and all the reflections. And that says that we, if we scale it so that this square root 65 will become 1, we would get quite a lot of unit distances. And it turns out, and this is a simple result in number theory, that if we replace 65, so the property of 65 was that it was a product of 2 primes, 5 and 13, and both of these primes are congruent to 1 modulo 4, namely give remainder 1 when we divide by 4. So if we replace it by a product of k such primes, then we will get a distance d, so that every point of the grid, which is not too close to the boundary, will be of distance exactly d from 2 to the k plus 1 other points of the grid. So if k is big, this increases, and if we optimize here the parameters, this will give us the example that shows that in the grid, if we choose the popular distance correctly, we get it n to the 1 plus c over log n times. Now, the grid points here represent, and now I'm starting to talk maybe more at the level of buzzwords, if you are not familiar with the notions, but I want to say it anyway. So the grid points here represent what is called the Gaussian integers, which are the integers in the number field Q of I, which is obtained from the field of rationals Q by extending it, by adding to it the purely imaginary number I, which is square root of -1. And these points form a lattice. This lattice contains many vectors of the same norm. And the set of lattice points inside, for example, square root n by square root n square, is a large planar point set with many pairs that determine the same distance. And in some sense, the construction that the model found is based on a similar idea, only everything becomes more sophisticated. So we replace, we start with what is called a number field of a higher degree. And we look at the integers in this field. So every word that is in red here is a notion that's a formal definition has to be given, but I'll just mention the buzzword. And the integers in these fields provide a high-dimensional lattice, And using what's called the Minkowski embedding, this lattice can be projected to the plane. So more precisely, and again, I'm not claiming here that this describes the proof, it's just at the level of buzzwords, but let me still say it. So the proof uses what is called a tower of totally real number fields, and it uses it to obtain a high degree fields over the rationals whose rings of integers under what's called the Minkowski embedding give some high dimensional lattices with a very large supply of special vectors coming from the fact that we have there many units, what is called units. And then a carefully chosen projection to the plane is then used so that many of these vectors are projected to vectors in the plane of length 1. And then if we take the projection of all the lattice points inside some large convex body, which can be a box or a ball, then we will get under the projection a large planar point set with many pairs at unit distance. So this is not meant to make too much sense, but let me just say that instead, so the example of the Gaussian integers, the field is just q of I, and the degree of it is only 2. The ring of integers there is what is called the Gaussian integers. The Minkowski embedding gives an embedding in dimension 2, and the units here are just the numbers plus minus 1 and plus minus I. And then because the Minkowski embedding gives already a lattice in dimension 2, we don't need a projection. We are already in the plane, so everything becomes simpler. And this is the previous construction. Here we have to use these things. And I want to point out that even if you decide to try this idea and you kind of know the area, this is still highly non-trivial. So there are lots of things that have to be done here. So you have to choose the correct tower. It's somehow not so intuitive really to take a growing degree fields, unlike the previous construction. And then you have to choose carefully the lattice, and there are all kinds of choice of parameters that have to be made. So even if you try this approach, it would be pretty easy to get convinced that it's not going to work. So you need a lot of patience. Okay, so let me now move to the speculations about the power of AI models in mathematics, and these are indeed speculations. So from now on, I'll be almost completely non-technical. And let me start with this quote of Mark Twain, and that's from something he said in a speech in 1882, so it's well documented. And he said that you may have noticed that the less I know about a subject, the more confidence I have, and the more new light I throw on it. So, kind of following the lead by Mark Twain, I'm going to try to sound very confident from now on. So, let me mention 2 points that the AI construction and proof in the solution of this unit distance problem, which was a spectacular result. And these are 2 points that show where the AI model seems to have a clear advantage over human mathematicians. So first, in the proof here, you really had to know geometry just to know something about the problem and about its background. And then you had to know pretty deep tools from algebraic number theory. And the thing is, the model knows all mathematical areas. Human researchers usually specialize in some specific topics. And in fact, some of the proofs in mathematics that we are most proud of when we find them is when we find a way to use tools from one area in order to get results in another area. But for the models, this is not a big deal, right? It just knows everything. It read basically all the papers that appear in the internet. It knows all the areas, and it knows all of them kind of equally well. So using one area to solve a problem in another is very natural for it. And another thing is that the model has more computing power and it's more patient, right? So it doesn't have to sleep, it doesn't have to eat, it can try. So as I said about this unit distance problem, even if you want to try the approach that the model really tried, you can think about it and try to play with it for an hour, a day, a week, or a month. And then usually after some time, if it doesn't succeed, then you convince yourself that it's not going to succeed. If the model has more time and more patience, he can try and this seems to be what happened here. Really, if you look at the chain of thought, so the model gives something about the way he was thinking, and you can kind of see how what he tried and how he thought about these things. Now, I should say that at the moment, it still seems that humans may be ahead in some cases. And in particular, there is a recent result by Blum, Sawen, Chilcrat, and Zelzov disproving another, variant, I should say, of a well-known conjecture of Erdős and Semeredy, but it's a variant. They didn't really solve the problem as it was called. And this is a sum product conjecture. And the result is that basically that there exists large sets of real numbers so that you don't get too many sums of pairs of numbers from the set and not too many products of pairs of numbers from the sets. And the original problem is the same question for integers, and this is still open. But I should say that really the construction here and the proof were inspired by the solution of the unit distance problem by the model. So you kind of use the same kind of construction to get sets that have some rich symmetries of multiplication and addition. And because of this, they have this property. And at first, when you see it, actually, they sent me the paper just before they posted it in the archive. So at first, you are happy that here human researchers were ahead. But then you look at the paper, and it includes the following statement that GPT 5.5 Pro was used as a sounding board in the early stages of the development of this proof. But the final proof, including all the main ideas, was almost entirely human-generated, the exception being the suggestion of lemma 3.4. So this still had some help with AI tools, and right, so it tells us something about the power of these models in solving problems. Now, I wrote here that mathematical research is not only about solving problems. It also involves asking interesting questions, suggesting worthwhile research directions, defining interesting notions, and judging the interest and value of new results. And at least at the moment, the main focus in mathematics of the existing AI models, all of them, is on the solution of problems and not about these other aspects. But I think it's not impossible that the models will also be able to perform these other tasks. And there are some initial attempts in this direction, more in the academy than in this commercial companies, but it looks that models can also suggest questions, and they can do some of these other things. So one personal guess I have looking at what is happening, and we just talked about 2 or 2.5 examples, but there are quite a few others. And it looks that it will become very difficult to obtain top quality results in mathematics without at least help by AI tools. So I'm not saying that they will solve all our problems independently, although that's a possibility also, but somehow it looks that using them can be very powerful and very helpful. And this raises several concerns. So it is very possible that one of the most important skills of a mathematician, and in fact any other researcher in other areas of science, in the future, and in the near future, I'm talking about the next 2 years, let's say, or 3 years, will be to know how to work efficiently and successfully with the models, how to prompt efficiently to ask the right questions and to work with them successfully. So we used to think that it's very important for a mathematician to know different areas, to know, to have a very good idea of what is known and what is known not, but this is now you can get it from the model for free very easily. So maybe, and it looks that indeed this is a skill to know how to prompt the model to ask the right questions. And one danger of this is that it looks, and probably many of you who tried to play with the models, it is always tempting to work with a model instead of trying to think independently. So somehow to think is a hard process. You have a problem, you think about it, usually you think for hours, maybe with no success, but you are sitting next to the computer. It's very easy to say, okay, let me not waste now 3 hours thinking about it. Let's just ask the model and see immediately what it thinks. And this is kind of dangerous. It tempts you to stop thinking. I don't know how many of you read these short stories, Aviv, published in 1950, so way before I was born, by Ray Bradbury. And this is really a science fiction and horror story. I'll not say what it describes. And I read it first as a teenager. And there I think I was more impressed by the science fiction or horror aspects of the story. But looking at it again last month, I noticed that really one of the main points there, and maybe this is what Bradbury was trying to convey, is to show how tempting it is for humans to gradually outsource or delegate their responsibilities to machines. So in that story, there are 2 parents, and they basically delegate all the house duty work and all the responsibility of the children to these machines. And in their case, it leads to a disaster, but you really see how tempting it is to do it. And it's the same here, maybe, with AI models, that, as I said, maybe it's sometimes very tempting to ask the model and not to try to think ourselves. But I want to end positively. So let me say that still, I believe it is unlikely that AI tools will completely replace human mathematicians. And in fact, even if they do so, even if the world will change dramatically, and it is changing already, but even if it will change more dramatically, there will, I believe, always be interesting opportunities for talented people And a training in mathematics or in science in general is a great general training. So if we enjoy it, then we should keep doing it independently of what we think about the prospective changes. And I try to answer in this spirit questions of graduate students and postdocs and young researchers who are asking me what they should do with all these developments. How would mathematics look in a year or in two? And I think that even if it will look very different, it's still a good idea, if you like it, to keep doing mathematical research. So let me say that we are surely living in an interesting world, which is changing rapidly. And we know about this apparently urban legend about this Chinese curse that says, may you live in interesting times, as a curse. And in Israel, we certainly live in interesting times, pretty much always in many respects. But although this is often used as an example of a curse, I think that here it will actually be really exciting to see how things will keep developing and to witness the impact of AI on mathematics, on science, and on life in the near future. And with this, I'll end. Thank you very much.
Thank you, Noga.
Mm-hmm.
So we have a number of questions in the Q&A section. So Noga, please tell us if you want to read them yourself or should.
Okay, so they appear in the chat?
Yes, in the Q&A.
Look, I don't see questions in the chat. Should I look in some other? So I'm looking
in the Q&A.
It's a Q&A.
Q. Right. So just a minute. Is it? So in the more, right? Yeah, maybe in the more Q&A. Good. Okay.
Let me use the opportunity.
Okay, I can read. So the first question that I see here by Itai is, can you estimate how many mathematicians all over the world seriously try to solve Erdős problems in a year by most known and less known problems? I can try to estimate, but I would think that especially since this web page of Blam came out about a year ago, then it's more people than before. So I would say that definitely hundreds, maybe thousands, depending on what we mean by seriously. So this would be. Here is another question. Will there be another lecture with the formal proof? So it's at the moment, I don't plan one. It's giving all the details of the formal proof would be quite difficult, and I don't think that it can be done in an hour lecture, even if you have some reasonable background. But it can be done, and maybe we would plan something. So let me say, here's another question. Could such grid construction give better upper bound for the distinct distances problem, hopefully improving? Okay, so this was asked by Shachar Smolodinsky. This actually, we talked about it among the people that wrote this companion paper to the unit distance problem. So I should say that Erdős, in the same 1946 short paper in the American Mathematical Monthly, where he raised the unit distance problem, he also raised the distinct distances problem, which is how many distinct distances endpoints in the plane must always determine. So is it the case that whenever we have endpoints, then we have many, many distinct distances? And the grid construction is believed to be essentially tight for that, and it gives something like n over square root log n. And for this problem, about 10 years ago, there was a solution by Gut and Katz, a very clever construction based on what is called the Elekes-Sharir framework and all kinds of sophisticated tools, polynomial method, and they proved it up to a factor of square root log n. Now it looks that that these algebraic constructions, it will be very hard or impossible to improve it, to improve the bounds that they know. So it looks that that the answer is probably no, or at least this is the feeling of the people who thought about it. Another thing that people were wondering about, there is another old problem of Hadwiger and Nelson about the chromatic number of the unit distance graph in the Euclidean plane. And the question was that maybe such a construction would be able to provide a better lower bound. And again, it looks that probably not. Let me go to the next one, Oren. How was the model prompted when it found the solution to the unit distance problem? So, and was it a large prompt giving a lot, maybe relevant context, or something simple like solve and how did this internal model differ from public-facing models? Okay, so I'll say what I know. So they gave us the prompt, and the prompt just described the problem. So it's not one sentence, the prompt, but maybe it's 10 lines, and it describes exactly the problem. It says that the known bounds are lower bound of n to the 1 plus c over log n, and upper bound n to the 4/3. And then it says to the model, don't give me any partial solution which is not answering the question if it's a power or not. Namely, don't improve the n to the 1 plus c over log n if it's not an improvement to at least n to the 1 plus c for some c, and don't improve the n to the 4/3 to n to the 4/3 minus epsilon, but really tell me a solution of it, and then this is what the model did. Now the claim is that this internal model is not very different from ChatGPT 5.5 Pro, and they claim that ChatGPT 5.5 Pro can now basically do similar things. And you see, the things are that these models, so as I said, like we started seeing proofs of research problems maybe in December last year. About a year ago, in July 2025, the models were good enough to get a gold medal in international mathematics Olympiads for high school students, which is pretty impressive, but you know, it makes sense that if you feed them all the problems that have ever been asked in previous Olympiads, then the problems that are being asked are similar. Then in December, we started to have some examples of solutions to problems. And in May was the first time that we had a solution of spectacular problems. So it keeps improving quickly. And it's hard to guess what will be the situation half a year from now. But okay, so I'm hoping that here is Iran Pasternak. Is the proof a combination of known results and
maybe can I interrupt? So there are about 30 questions. So feel free to choose whatever you want to do.
Okay. So I try just to go. Okay, I see. So shall I take the ones that look shorter? Let me. Okay. Let me still answer this one. Is the proof a combination of known results and techniques, or did it introduce a new lemma, notion, or methods? Is the proof itself useful, providing tools for more proofs? So I think it is a combination of known techniques, but it's a very non-trivial combination of known techniques. And then you still have to choose the parameters right and to do it in the right way. And the second is the proof itself useful? So as I said already, this led to a solution of this sum product problem for the reals. So definitely the proof itself is useful. And I want to say that the fact that the proof is a combination of known results is not many of the most impressive proofs by human mathematicians are when you kind of take known results or known techniques from different areas. Maybe you combine them, maybe you add, so it's not very different. Of course, there are also some things where we really have to invent new mathematics, and that did not happen anymore. Okay, so now I'll go down and I'll pick only the short questions. Okay, so Anonymous, is it okay? Or you try to say something?
Can I ask some questions here from the crowd?
Okay.
A small question I want to ask is about which type of problems do you recommend, okay, to use AI? And there are many types of proofs also. This proof can be considered maybe a constructive proof. Yeah. Other type of proofs you think that AI can solve, like contradiction or something like this. And if you have a problem in mind, an open problem that maybe you want to...
Okay, so I think at the moment it looks that it's particularly good in questions where you need some complicated optimization, that the model will be better than man because you can do bigger computations, and it looks that it's very good in finding counterexamples. But and so far, because indeed they looked a lot at Erdős problems, there are many results in number theory and in combinatorics. But I do hear from people that already got results, just a proof of a lemma that they didn't know, or so in symplectic geometry, in pretty much any area. And again, I would think that at the moment it's indeed better in some areas than others. But if I have to guess, I would think that it would be able to contribute to pretty much every area. And in particular, I mean, it's not that any question we ask it solves, but kind of communicating with it, it looks that it can be very helpful. I should say, by the way, that still often it says complete nonsense, it invents things, it says wrong things, so you definitely have to suspect it and to check everything very, very carefully. So it's not that you should trust it. You should be very suspicious, but still it is useful. Now I'm looking at, here is a short question. Did OpenAI received $500 for solving unit distance problem? This, I'm sure that this will change the whole value of the company if they go to the public now, because the expected value is between 500 billion and a trillion. So now I think it did not get, I would think that it did not get, so there is someone who is still taking care of paying some of the Erdős promised prices. He has, there was some small estate, and for a while Ron Graham was doing it. Now there is a mathematician in Iowa State called Steve Butler that is handling it. And he was giving some prizes to human mathematicians for solving problems long after Erdős died, but I don't think that here the model really needs this, and I don't expect that they will get it. Here is another short question. I would be interested in hearing why you think that the talented people will still have interesting opportunities. Well, I think that talented people will always have interesting opportunities. I think that no matter how the world will look, then talented people will have more opportunities than dumb people, if I have to be. But of course, this is also a speculation, but this is what I think. I mean, I'm looking. So at the moment, I don't mind staying here as long as we need. At the moment, there are still more than 300 people in Zoom. So definitely, I will keep staying here. But indeed, I'm going down, trying to find relatively short questions. Okay, here is one by Danny Vlenchik. Do you think that one advantage of AI is the fact that it's not biased? It's not primed to think in a certain way, and so it can be creative. It's possible. I mean, definitely, when you look at the chain of thought for the unit distance problem, you almost get an impression that it had the right intuition. So somehow, very quickly, it went to the counterexample and not to the proof. And there is also a question of what exactly do we mean by being creative. So usually we find an original or a creative proof. Usually this means that it reminds us something that we've seen before, and it's so it's not completely clear that human mathematicians are more creative than models. I should add again, by the way, that all my remarks about the potential of AI models in mathematics are kind of guesses, right, and speculations, and any one of you is welcome to make her or his own speculations. Here is another short question. Are there particular tools you are recommended for mathematicians to use? So probably I should not promote any of the companies. I mean, like, my own impression at the moment is that for mathematics, ChatGPT is or OpenAI is better than say Anthropic or Claude. For programming, I think it's well agreed that the Anthropic is leading. Also, the Google Alpha is not bad. I would expect that all of them would be good. I think that I saw today that Apple is now entering. So it looks that if you are a huge company that is willing to invest billions in these LLMs, then and you care about mathematics, then the models will be good. I think that at the moment, ChatGPT is the best one. I should say, by the way, that it's not impossible that these commercial companies will decide at some point that they are not interested in mathematics, that the commercial value is limited, and that is something that may stop the progress. So the fact that such huge amounts of money are involved here will really influence things. Well, there are some very long questions, so I apologize, but I will skip them.
I would like to skip the line and ask a follow-up question.
Okay. So say that again. So you like?
The question is whether you yourself are using LLMs these days, and if so, when you started and what prompted you to do that?
Right. Yes. So I now have this Chat GPT Pro 5.5 because usually when you know these people, they give you access for free. So but I started using it myself only maybe in February, and I did not use it. I've not used it seriously yet. Maybe I'm the wrong generation, or maybe I still want to feel that I keep thinking myself. But I still used it enough that it was useful, not only in giving references and but even in suggesting in some directions, in proving some lemmas. My impression is that so far for me, it didn't do anything that I couldn't have done myself, but it saved time. I do have in Princeton at least one graduate student who is using it more seriously, and he already obtained some really nice results where the AI tool kind of played a crucial role. So people are now publishing papers all the time where they say that this was done with help of this and this AI tool. Probably people are also publishing papers where they did get a lot of help by AI tools and they don't admit it. So there is a trouble that it's hard to enforce it. And this is also one of the troubles that all this program, these developments raise, that it's hard to know what was done by humans and what was done by AI tools. And with AI tools, you don't often get the right credits. So, these LLMs, they read everything, they know everything in the internet. They provide solutions to something they ask you. You ask them, sometimes maybe it's really a solution that they found existing in some paper, or just a very small modification of something that they found in some paper, and they often would not give a proper credit. Sometimes maybe they don't even know where they found it. So they kind of read everything, they know everything. So this is also problematic. So should I keep reading or should I? So here is a short question, which is, will not AI enlarge the number of mistakes using wrong results? This is certainly a danger, and people are aware of it, and we have to be careful about it. I don't know how many of you saw, a few days ago, there was something called the Leiden Declaration, which is an announcement by several mathematicians and computer scientists, and it was endorsed by the International Mathematical Union. And there people write something about the dangers of using AI and about the way we should use it if we use it. And this was already endorsed by lots of mathematicians, and if you read what some of them wrote, you see that really some of them more or less tell you that we don't want to use them, and we think it's bad to use them, but I believe it's too late. So I don't think this can be stopped. So of course we have to be very careful about it. But somehow, at least so far, mathematics has been robust. You may worry about. Definitely, there are papers also, and there have always been papers that are wrong, that contain wrong results, and have been published because someone missed it. And at least theoretically, once you have a wrong published result, then you can use it to prove everything, right? Because something that is wrong implies everything. And still, somehow, this does not happen. It looks that mathematics is robust, or at least has been robust so far. So the hope is that the AI will not enlarge the number of mistakes, but I agree that we have to be careful about it. And those AI tools have a very impressive ability to write wrong proofs in a convincing way. So definitely you have to be careful when you use them. So here is another question, and I thought about it also by Alec Weinstein. Do you think that human mathematics can turn into a kind of sport like chess? So you see, this, I hope not, but this may happen. You see that in chess, we know that now computer programs are far, far better than the best human chess players. And in fact, these AlphaZero chess programs, what is even more disturbing is that you don't even teach the computer to play chess. You just tell the computer the rules, and then the computer, knowing the rules, plays with itself for a few hours, improves itself, and after a few hours, it will be better than any other human chess players. And still, people play chess, right? There is world championship, and so we still do it. And you can say also people compete in 100 meters dash. Machines can run much faster than humans, but this didn't disturb us. So of course it may happen, I hope it will not happen, that the machines will be so much better than humans in all kinds of mathematics. That's the only reason to do mathematics will be some kind of sports. You'd have these puzzles, you would know that the machine can prove it. Let's see if I can also solve Riemann hypothesis after the machine did it. Well, I hope that this will not be the case, but I agree that this is also maybe something that we have to worry about. Should we? Okay. I see here a very short question, but it only says I meant n over log n, so it refers to something previous. I don't really know what the question was. Here is Yuval. How should mathematicians train to use these models themselves and their graduate students? At the moment, it seems that that we can just use it and see what's going on, and it looks that that the younger generations, like graduate students, are at least far better than me in doing it. Right, yeah. So probably just by using these models ourselves, we get better in doing it. Okay. Here is okay. I see here a message. Maybe this could interest some of you. So there is a message by Chaya Keller that there would be a lecture by Uzi Vishne about the technical proof, and this would be on Thursday in Bar Ilan, and there is also a Zoom. So I'm sure that if you just write Uzi Vishne lecture about the proof, you will be able to find it. As I said, really understanding all the details. So it depends how he's going to do it. Uzi is a very good lecturer. And the question is if he would would choose to sketch it or to really show most of the details. But I'm sure this will be interesting. Right. Okay. Should I keep going down, or you want a question from who works in OpenAI to verify and interact to obtain this proof? So there are. So this was a question of Mirav Zahavi. So OpenAI has been really successful in hiring some great mathematicians, like really people who were among the very best, and that some of them had already tenure jobs in top universities in the US. So I can let me not name specific names, and they really interact with the model, but still, so sometimes they are able to verify it themselves. In this case, with the unit distance, what they chose to do is to send it. So they kind of more or less convince themselves that it looks believable, but then they sent it to about 10 mathematicians that were more in the area, asking to verify it and to make comments. But they have a very good group of mathematicians, and I think that they are still hiring. And the thing is, it's an industry. If you want to work in industries, they can. They have some disadvantages, but they have also, of course, advantages, big advantages on what they can offer in terms of compensation. But luckily, I don't have to worry about this. Okay. Is there progress on the problem in R3? That's a nice question. So one can ask about the unit distance problem in R3. Actually, there is a dramatic progress, maybe it's not public yet, about the distinct distances problem in R3. So that's nearly solved now. On the unit distance problem in R3, at the moment, I don't know anything new. And of course, the unit distance problem becomes kind of trivial in dimensions 4 and more, or uninteresting. Okay.
The question by Vera can be interesting.
Yeah, I see here. Yeah, I see another very short question where I can. So can AI check proofs? So it's it's reasonably good in checking proofs. People try to use it, so to take proof from one system and give it to another, or there are also systems that send it to Lin that make a formal proof. We had one specific case that we got some submission to the Annals of Mathematics, which is a very prestigious journal, and it's handled in Princeton, and they asked me to look at it, and it looked suspicious, but it looked that it would be difficult to check it, and I gave it, actually, I asked some student to help me, so he gave the proof to this AI, to ChatGPT, telling it that there is an error in section 3. I suspected that there is an error in section 3. Can you find it? Because it's not so good to ask it, is there an error? So it's better to tell it, there is an error, find it. And then it really told us where the error was, and at least in that case, it was right. And I suspect that this may become a must, because there would be, at least in the near future, there would be more papers, I think, generated with the help or by AI, and maybe the only way to handle them would be to be able also to check the proofs by AI. Yeah. Okay. Someone here is telling me, and maybe it's right, that בעברית, so I apologize for the non-Hebrew speakers, let me read it in Hebrew. רק נקודה קטנה, כי בדבריך כרכת מתמטיקה ומדעים אחרים יחד, ייתכן שהם שונים בכך שמתמטיקה במידה מסוימת סגורה על עצמה, בעוד שהמדעים נסמכים על תגליות ניסיוניות פתוחים לתגליות חדשות. So this is about the difference between mathematics and other sciences, and especially experimental sciences. And I think it's true that these AIs are more powerful, and it's easier for them to do mathematics because it's everything there is kind of well-defined and formal. But on the other hand, let me tell you that I talked with some experimental physicists in Princeton. Just I met them at lunch one day, and they were telling me that they use AI seriously, so they try to ask it to suggest experiments, and which experiments should we do in order to check this and that. And they did say that so far it was not indeed dramatic, but they said that it's helpful. So at least it is the case that other sciences, including experimental sciences, are at least trying to use these AI tools. It could be that that this will take longer, or that maybe they will never be able to do it. I now kind of find it very difficult to predict that something will be totally impossible. In fact, if you want an anecdote, I have a good friend in Princeton who is a historian. So he's in the institute. He's a historian, a well-known historian. He's kind of older, so he used less computers also as a historian, but somehow we were talking recently about this, and he told me that he's sure that these models will never be able to replace a historian. So I only smiled. I mean, it looks to me that, they just have to read all the history, maybe now technically not everything appears in the internet, but this is just a technical problem, and then to summarize it and make conclusions, I don't believe that this is something that only a human can do. But again, these are just my own opinions. Shall I keep? Do you think the paper reviewing process would be completely taken over by AI in the near future? I think that not. That still we would want to have people involved. At least, definitely, people involved in deciding what is interesting and what is not. And I have here another question, which is a good question. Is P equal NP the next one to be resolved? And if not, why? So, probably not, but just because this is the answer on any well-known problem. And this solution of the unit distance problem is a spectacular result, but probably the models tried to solve 50 other important problems and didn't succeed, right? So we see only the successes, and therefore, if we fix a specific problem like PNP or even something less important, I think the chances it will be solved in the near future are slim, but I would hesitate to say zero. But if, for example, we would say there is this list of clay open problems, that one of them is PNP, and then there are 6 or 7 other problems, equally important, Riemann hypothesis, Navier-Stokes. I'm pretty sure that they are trying to run the models on them. It will not be shocking for me if in a matter of 2-3 years, one of these problems will be solved by AI. Again, it's just speculations. What I'm completely sure, and these are not speculations, that AI will solve more problems that are kind of interesting problems in lots of mathematical areas. Would it really settle something like PNP or Riemann hypothesis? Well, I don't know. This is harder. And I don't know to answer. So I have here a question: which of the clay problems do you think is more suitable for LLMs? I don't have a good answer for this. But yeah.
I think there's a balance on impact specific questions or fields. So feel free to answer all of them or none of them.
Right. So I see quite a few on which I don't know to answer. Do you think AI can solve Collat's conjecture? Well, like any other, I mean, maybe, or why not? So again, it's a question that many people thought about for a long time, and so it's probably difficult. It will not, it's hard to know, although it's a well-known problem, and many people thought about it. It's, in some sense, maybe it's not such an important problem. It's not clear if it would have, well, it depends on the solution. It's not clear if it will have many consequences. I don't know.
Okay, let me maybe highlight the final question, which is what do you think is the right answer for the unit distance problem?
Right, yeah. So of course, there is a huge gap still between the lower bound that is now maybe n to the 1.014. So this is optimization of Will-Sawin of the AI proof. Some people actually say that AI already improved the constant a little bit in the Sawin argument, but but still there is a big gap between, because the upper bound is n to the 4/3. And the question is, what is the right answer? I definitely do not think that the right answer is n to the 4/3. There are already all kinds of suggestions of ways to possibly improve it, and somehow the n to the 4/3 does not use much of the specific properties of the Euclidean distance. The same proof works for any norm, which is what is called strictly convex norm, where for this version of the question, there are norms for which the n to the 4/3 is tight. So I would think that it's some constant between 4/3 and n to the 1.01, and maybe like in many interesting problems, it's some constant. It's not a nice constant. It's some numbers that will appear as optimization of some type of construction. It's not impossible that the best construction is some algebraically based construction like the one found by the AI, because at the moment it looks that all the good construction has some sort of an algebraic structure. Right. Okay, so we are now at 179. I can...
We were at the peak, we're about 500, and I think this is a good point to wrap up. So thank you very much, Noga, for this excellent lecture and for this.
Okay, and thank you very much to all of you for participating, and I hope next time to speak in person and to see some faces and not only the computer screen. Okay.
Okay, goodbye, everyone.